Module 8 Investigation 5, the Law of Sines. Consider the 9-right triangle ABC as shown below, with side lengths lowercase a, b, and c, with altitude BD whose length is h. Write an expression that calculates the value of h if the measure of a and the length of c are known. So, notice that h is opposite of angle A, c is the hypotenuse. We can use sine of A equals h over c, or simply h equals c multiplied by sine of A. Write an expression that calculates the value of h if the measure of angle C and A are known. Well, same sort of thing. The sine of angle C will equal h over A, or we can just write h equals A times sine of C. What do the results in parts A and B tell us? We can calculate h using, let's see, an angle and a side. It's hard to know exactly what this question is asking us to do, but notice that both of these expressions equal h. So we could set them equal to each other. C times sine of A would equal A times sine of big C. Then we could rearrange this by dividing both sides by C and both sides by A, and we'll have sine of A over little a equals sine of C over little c. And this is getting to something called the law of sines. Now suppose we draw the altitude CE whose length is k. Write an expression that calculates the value of k if the measure of angle A and B are known. So I'm thinking we'll again use sine of A. And what would that be? K over B. Since we're looking for the value of K, I'll just write it like this. B times sine of A equals K. And then if we use angle B, the opposite over hypotenuse, K over A, we'll just again have K equals A times sine of B. And then if we put those together, that means B times sine of A equals A times sine of B. And then we could rearrange this to get this. Since the triangle in problem 1 was a generic triangle, no specific side lengths or angle measures were given, our conclusions may generalize to any triangle. This generalization produces the rule known as the law of sines, which is summarized below. So essentially, this tells us that the ratio of the length of one side of a triangle to the sine of the measure of the opposite side is constant for each side of the triangle. Use the law of sines to find the value of x in each of the following triangles. Now let's see, here's x. I know that x over sine of 82 will equal 42.7 over the sine of 34. That means x equals 42.7 over sine of 34 times sine of 82 degrees, of course. That gives us 75.62 inches. Now let's find x here. We know by the law of sines that x over sine of 28 equals 19.82 over the measure of angle A. And then the measure of angle A is, of course, 180 minus 50 minus 28, which is 130 minus 28, which is 102. So I'm just going to replace the measure of angle A here with 102. Wait, not 102. Sorry. Should have been sine of A, or sine of 102. That means x is 19.82 multiplied by the sine of 28 degrees over the sine of 102 degrees. That's about 9.5 feet. Use the law of sines to find the value of x and y in each of the following triangles. Let's see, x over sine of, oh, that's not right, x is the angle now. So 4.11 over sine of x will equal 6.32 over sine of 83. If you're confused, then refer back to this law of sines that I'm using here. And I apologize again for writing a instead of sine of a right there. Okay, so we need to solve for x. Let's see, we could like cross multiply or something. 4.11 sine of 83 equals 6.32 sine of x. That means that we can divide by 6.32. So 4.11 sine of 83 over 6.32 equals the sine of x. That means that x can be found with the inverse sine, or the arc sine, of 4.11 sine of 83 over 6.32. Okay, and I got 37 degrees, 40.2 degrees. Well, that means that we can find angle C, 180 minus 40.2 minus 83, get 56.8. So that means y over sine of 56.8 equals 6.32 over sine of 83, which means y equals 6.32 sine of 56.8 over sine of 83. And I got 5.32 centimeters. So the new thing about that problem was using the inverse sine to find angle x. Okay, so now let's find x and y once again. Let's see. So 2.5 over sine of x equals 4 over sine of 37. That means that 2.5 over 4 sine of 37 equals sine of x. So if we take the inverse sine of all this, we'll get x. You might need to work that out on paper if it's not clear. Okay, I got x is 22 degrees. So that means that this angle B is 180 minus 22 minus 37, or 121 degrees. And now we can find y. Y over sine of 121 equals 4 over sine of 37, which means y equals 4 times sine of 121 over sine of 37, which is about 5.7 feet. In many cases, the law of sine works perfectly well and returns the correct missing values in a non-right triangle. However, in some cases, the law of sines returns two possible measurements. This is the case in the triangle below. So they've already done the process for us. 4.19 over the measure of angle C equals 3.93 over the measure of angle B. And they've solved for the measure of angle C. Actually, they've solved for sine of the measure of angle C. Then they've taken the inverse sine, and they note that it's possible to get two answers. And they leave it to us to decide why. Well, let's just calculate that one and see what the big deal is. Okay, so I get 68.83 degrees. Let's look at our triangle. So if we don't assume that this is drawn to scale, I think that our issue is as follows. Like, this looks like 68.83 degrees, no problem. But what if C was actually an obtuse angle? We could have all the exact same measurements with an obtuse angle. Like, we could have 4.19 here, 3.93 here, and 61 here. And we could have just not gotten the right. So to find the other possible one, let's do 180 minus 68.83. Get 111.17 degrees. if we assume that it's drawn to scale, then 68.3 is the best one. I think I learned about this thinking about a triangle like this. Like, it could be that we have this sort of situation here. Here's angle A, but if angle B got swept out over here, let's see, well, angle A wouldn't change, but notice angle B here, it's obtuse, but here it's acute. And if we use the law of sines with either the obtuse or the acute case, it'll just give us the acute angle, because our calculator, it gives us the inverse trig function, which we know is restricted. So we can't, like, the calculator won't give us the obtuse case. We have to take our answer and subtract 180 from it to get the obtuse case. Yeah, I don't know if that helps, but yeah, here's again sort of a description. Like, B is obtuse in this case, but if we applied the law of sines, we wouldn't get an obtuse angle, we'd get an acute angle. And so notice that we'd actually get this angle, but to find the other one we need 180 minus this one. So maybe that helps. Oh, if we assume the drawing is more or less to scale, then of course this one, 68.83 degrees, makes sense. Use this value of measure C to determine the remaining measurements of the triangle. Okay. So we can find this angle here. That is 180 minus 61 minus 68.83, because all the angles, the sum of the angles of a triangle is 180 degrees. The only thing missing is this side BC, and BC over sine of 50.17 degrees will equal 4.19 over sine of 68.83 degrees. And so BC equals 4.19 times sine of 50.17 over sine of 68.83. That is 3.45 centimeters. Determine the dimensions of the second possible triangle with the given measurements, then draw the triangle approximately to scale. Alright, so that second possible triangle had 117 degrees here. That means the other one, the other angle, is 180 minus 117 minus 61. Was it 117 or 111.17? I think it was, yeah, 111.17 actually. So again, 180 minus 111.17 minus 61, 7.83 degrees. Then we're just missing this side. We can call it BC. So BC over sine of 7.83 degrees equals 3.93 over sine of 61 degrees. So BC would be 3.93 divided by sine of 61, and then multiplied by sine of 7.83 degrees. 0.612 centimeters. So this isn't drawn to scale exactly. This angle should be very small, and then this side should be much smaller, so we really have something like this. That's pretty horrible. Draw the triangle approximately to scale. I'll try one more time. Okay, that's the best I can do. There are two possible triangles with the given measurements shown below. Find the measurements of both triangles and draw each triangle approximately to scale. Let's see. So let's try it like this. Imagine that we have another triangle with this same length AB here, but instead of the 7 side length coming down this way, it goes this way. So that this is 7. Now our angle C would be much larger. It would be an obtuse angle. So there's really two possible triangles here. It seems kind of weird, but if we're just talking about the measurements we have, meaning an angle right here of 29, this length of 13, and this length of 7, those are the only measurements that we have, then the first triangle we could have is already shown for us. But then the second one would be that blue one. Really, I should add this piece too. Okay, so here's our two possible triangles. Okay, now let's find all the measurements. So here, what can we do? Let's find the measure of angle C. 7 over sine of 29 equals 13 over sine of C. That means sine of C equals 13 over 7 times sine of 29. And we can say C is the inverse sine of 13 over 7 sine of 29 degrees. 64.21 degrees. Then angle B will be 180 minus 29 minus 64.21, 86.79. So then, let's see, AC over 13, no, that's not it. AC over sine of 86.79 will equal, say, 13 over sine of 64.21. Solving for AC, 13 times sine of 86.79 divided by sine of 64.21. And now we've solved this triangle. solving the triangle, that sounds kind of funny to say. We found all the measurements. Okay, now how do we find this new angle C? Well, note that this angle C that in the bottom triangle is just this one, and that's a linear pair. We just need 180 minus 64.21. That gives us 115.79 degrees. Okay, now the other angle, 180 minus 29 minus 115.79, that's 35.21 degrees. Now the only thing missing is AC, so AC over sine of 35.21 degrees equals 13 over sine of 115.79 degrees. Notice what we also could have set that equal to 7 over sine of 29. But we get AC is 13 times sine of 35.21 over sine of 115.79. So now we've found all the possible measurements for the two possible triangles when we're given one side length 13, another side length 7, and an angle of 29.